Let's look at systems of linear equations. A linear equation is an equation of the form a1x1 plus a2x2 plus plus a sub n x sub n equals b. For example, is this a linear equation or not? You bet, that's a linear equation. 3 times x1 plus 2 times x2 equals 0. How about 5x minus 12y plus z equals 1? Yes, that's a linear equation as well. A constant times x plus a constant times y plus a constant times z equals a constant. 3x squared plus 8 equals, no, this is not going to be a linear equation. You can't have an x squared. It's not linear. 6 square root x plus, no, same story. Can't have a 6 square root x. That's not a linear equation. X plus y plus 3 equals 0. Yes, that's linear. You could just move the 3 to the other side, make it negative 3, and you'd be good. 4xy equals 1. Nope, can't have x times y. 8x equals 0. Yes, that's linear. Kind of boring, but it's linear. What we will try to do is solve systems of linear equations. We will look for a solution or solutions that satisfy all of the equations. For example, find the solution of this system, x plus 3y equals 7, 2x minus 5y equals negative 8. Let's use elimination. Multiply both sides of the first equation by negative 2 and add it to the second equation. Here's why we do that. When you multiply both sides of the first equation by negative 2, like this, okay, you're going to end up with negative 2x minus 6y equals negative 14. Then, when we add the second and the first equation, the x's cancel out, and we're left with negative 11y equals negative 22. Now, divide both sides by negative 11, and we end up with y equals 2. Plug into one of the original equations to find x. X plus 3y equals 7, x plus 3 times 2 equals 7, x plus 6 equals 7, that means x equals 1. The solution is 1, 2. X equals 1, y equals 2. Here's what that represents geometrically. The graphs of x plus 3y equals 7 and 2x minus 5y equals negative 8 are lines. We are looking for a point that fits both equations. That is, a point which is on both lines. So when you graph these lines, x plus 3y equals 7 in red, 2x minus 5y equals negative 8 in blue, there's only one point that's on both lines. The point where the lines intersect is at 1, 2. We can solve systems of equations using matrices. First, we represent the system x plus 3y equals 7, 2x minus 5y equals negative 8 using a matrix. Again, a matrix is a rectangular array of numbers. This is an augmented matrix. The matrix with just the coefficients is a coefficient matrix. So notice this one has the 7, negative 8 in the last column. This one does not. It's the coefficient matrix. This one's the augmented matrix. Why do we use matrices? We can solve it through certain matrix manipulations. That is, we can solve the system of equations. The goal is to use elementary row operations to get the matrix into a certain form so that we can see what the solution is. Here are elementary row operations. Interchange two rows, multiply a row by a non-zero constant, add a multiple of one row to another row. Elementary row operations do not change the solution of a system of equations. Let me show you why. Interchange two rows. So let's say interchange rows 1 and 2. That would take this augmented matrix and replace it with this augmented matrix. Well, that's the same as interchanging equation 1 and equation 2. You're just interchanging the order of the equations. That's not going to affect the solution to the system of equations. So interchanging two rows doesn't change the solution. How about multiplying a row by a non-zero constant? 10r1, 10 times row 1. In terms of matrices, that will replace this matrix with this matrix. You're just multiplying row 1 by 10. That's the equivalent of taking this system of equations and replacing it by this system of equations. Well, x plus 3y equals 7 is really the same as 10x plus 30y equals 70. That's not going to affect the solution to a system of equations. So multiplying a row by a non-zero constant has no impact on the solution. How about adding a multiple of one row to another row, like negative 2 times row 1 added to row 2? When we take this row, when we multiply negative 2, when we multiply this row by negative 2 and add it to the second row, we end up with this matrix. That's the equivalent of taking this system of equations and replacing it with this system of equations, as we did a moment ago. That's not going to affect the solution of the system of equations, because anything that's a solution to this is going to be a solution to this. The augmented matrix 1, 3, 7, 2, negative 5, negative 8 is a 2 by 3 matrix. Those are the dimensions of the matrix. The first number, okay, the 2 here, that's the number of rows. And the second number, the 3, that's the number of columns. How will you remember RC? RC. RC Cola, Roman Catholic, remote control, RC. Let's solve this system using algebra and using matrices. This is the system we saw a moment ago. So first, let's represent it as an augmented matrix. 1, 3, 7, 2, negative 5, negative 8. Let's do what we did earlier. Let's replace row, let's add negative 2 times row 1, and let's add that to row 2. So negative 2 times row 1 added to row 2. We've done this before. Multiply row 1 by negative 2 on both sides. That's the equivalent of multiplying this row by negative 2, okay? I like to write it above. So negative 2 times 137, that's going to give us negative 2, negative 6, and negative 14. And now let's add it to row 2. So when we add this to row 2, first row is the same, 137. Now row 2 is going to be negative 2 plus 2, which is 0, negative 6 plus negative 5, which is negative 11, and negative 14 plus negative 8, which is negative 22. So we end up with, algebraically, we just ended up with negative 11y equals negative 22. That was the result of doing this, okay? Matrix-wise, we end up with this matrix, so the equivalent would be multiplying row 2 by negative 1/11. And when you do that, you end up with 137,012. So here's our matrix. Here's how we solve it from here. We're just going to take it from here. We're going to express it algebraically. So this is the system x plus 3y equals 7 and y equals 2. So let's just back substitute y equals 2 into the first equation. X plus 3 times 2 equals 7, x plus 6 equals 7, x equals 1. So when you end up with a matrix that looks like this, you can just express it algebraically and use back substitution. The solution is 1, 2, as we've seen before. Find the solution of the system x plus 3y equals 7, x plus 3y equals 8. There's no solution because x plus 3y can't be both 7 and 8. We say the system of equations is inconsistent. It has no solution. The previous system of equations had a solution, so it was consistent. Here's what that represents geometrically. The graphs of x plus 3y equals 7 and x plus 3y equals 8 are parallel lines. They never intersect, so there is no point on both lines. Yeah, good luck finding a point that's on both lines. You're not going to do it.